everybody, my name is Divya Agrawal, and here I am presenting my second lab for Physics 2212, Charge Tape Revisited. Here's a little brief overview of our content today. Here's an introduction. The purpose of this lab was to produce a computational model of two charge tapes exerting an electric force on each other, and use this model to estimate the amount of charge on each tape necessary to float above the other. GlowScript I used to model the charge tapes and simulate the forces on them. Here is a brief overview of our results. So from last lab, we have the point charge on each tape being 9.53 times 10 to the negative 10 coulombs. And the lines of charge, the total charge on tape being 2.1 times 10 to the negative 8 coulombs. So, I'm going to be honest, our data for the point charge, or our calculations for the point charge, must have been incorrect because the difference between these values is a little bit more than it should be expected, and I talked with the group and they said that all the other people in our lab and everybody had different values, so maybe that's just something that we messed up on. Here are the fundamental physics principles. Newton's second law is important because it shows the change in momentum is proportional to the net force applied. This is important for force balancing and the balance between the gravitational and the electric force. Coulomb's law obviously shows the force between two electric charges, so the force between the two tapes. And then the gravitational force is important because it's the other force. So we're basically balancing these two forces out in this lab. Here are my results from lab 1. So this is the one before. So some brief overview, we have the tape mass, length, and then the distance. So the value that we got from this is 9.53 times 10 to the negative 9 coulombs. That's just important in this next lab. Here's my computational model. So here's some of the code. We had the E-field vector calculation, which was similar to what we did in the lab 1. And then we basically have a loop of each point charge, or like in the line of charge, for the simulation in lab 2. So we're basically kind of doing a similar thing for to find the electric field at each point, and then we're sort of summing that for the sum net electric field and force. Here are my results, and what we did for this, since the initial input of the charge was way too less for the magnitude, me and my lab group, we kind of just experimented with different values, and we ended up at that 2.1 value. And this is about correct. So we have 1.94784 times 10 to the negative 3 for the electric force, and then we have 1.85409 e to the negative 3 for the gravitational force. So we talked to the lab TAs, and they said that it was enough in the error range for it to work. And you can see how each of the individual charges go through, and then they sum up to there. Here are some assumptions and errors that we had in our calculation. So assumption 1 is that the air resistance and friction are negligible. Assumption 2 is that the charge on each tape is uniformly distributed, and assumption 3 is each piece of tape has the same charge. So obviously in real life, this would not be true, right? Because everything is not arranged absolutely perfectly due to entropy and like nature. So the errors that may have caused some difference in results from the actual values in real life could be inaccurate measurements during the experiment. So when we used the ruler to measure the distance between the tapes, we could have got that wrong, which would actually factor in a large amount to the gravitational force because the distance is squared and something even small could turn into a big thing. Another error that could be a huge loss of data could be loss of charge due to poor handling. So every time we touch the tape in our experiment, we were kind of transferring the charges between our hands and the tape, which was because in nature things want to go to equilibrium. And this was sort of diluting the charge on the tape, right? So it was not initially what we thought it would be, and the experiment results would have changed over time with the same piece of tape. Questions and conclusion. So, what if the tape was a point charge? Let's compare values. If the tape was a point charge, then the charge on each tape would be 9.53 times 10 to the negative 9 coulombs. As we have previously discussed, this value may be wrong, as it's not even remotely close to our lines of charge module. Our line of charge model shows that the total charge on the tape is 2.1 times 10 to the negative 8 coulombs. And maybe if we did the point charge experiment differently, then our value would be closer, but the estimates would still differ, and that kind of leads to the different question. So, which value is more likely to be accurate? I would say, the estimates differ because there's a different position in calculation, because the line charge model spreads out charge to represent a more realistic model, right? Because there's more charges, and in reality, there's so many electrons, so many neutrons, so many protons on these bodies that it's hard to replicate simulationally with something so basic like GlowScript. So this leads us to conclude that because the line charge model spreads out charge, the line charge is more likely to be accurate. And if you compare our lines of charge value with your lines of charge, you may find a similar value, but the point charge may be a little off due to some error in calculation. Thank you. Side note, I know it's Super Bowl today. Have fun. Go Eagles. We hate the Chiefs. Thank you.